Okay, hi everyone. This week we're talking about Atkins 17E, deriving rate laws. This is an example I showed you at the very start of this chapter. It concerns the formation of hydrogen and bromide gas. If you measure the rate law, right, it turns out to have this rather complicated form that looks like this. And that rate law arises from this proposed mechanism. Right? This is the mechanism by which hydrogen bromide is believed to be formed for this reaction. What we're going to talk about is essentially how you get this formula, right? How you use this mechanism to derive this formula. And we're going to start with just some terminology. These individual steps of the mechanism are called elementary steps. And what's important about elementary steps is that they are mechanistic descriptions of intimate encounters between atoms or molecules. In other words, if I write an elementary step, bromine plus hydrogen goes to HBr plus hydrogen, I am saying that a bromine atom is interacting with hydrogen to form HBr into H. Okay? I'm saying that these things actually come together and form a chemical reaction. And that has a number of important consequences. Number one, because elementary steps are mechanistic descriptions, they can be used to write rate expressions. So here's an example. If I had I'm going to sneeze. Oh, excuse me. If I had a simple elementary step that was A going to P, the molecule just transforms. The rate for this is minus dA dt, and that is equal to K times A. Because there's only one molecule involved here, I can write that this is a simple elementary first order rate law. Right? I can write a rate expression for this. I'll point out to you that the way that we usually write this is in terms of the disappearance of A. So we usually write this as dA dt equals minus Ka. It's minus because we lose it in this step. If the rate law were A plus A going to P, the expression for this would be minus Ka squared. Because two molecules of A react, right, it has a second order rate law. Got a little cut off there, but we actually don't refer to reaction order with elementary steps. Instead, we call it molecularity. So if you look carefully, you might be able to read this. The molecularity refers to the number of molecules that are involved in an elementary reaction step. So the first one, where there's just one molecule, would be referred to as a unimolecular reaction. There's only one molecule in the elementary step. This is a bimolecular reaction, right? Two molecules involved in it. So this is analogous to reaction order, right? And interestingly, we often don't see elementary steps with molecularities greater than 2. Why is that? Well, if you think about it, remember that an elementary step is a mechanistic description. Right? Two molecules come together to form something else. If you had a molecular of 3, it would be 3 molecules coming together. I don't have enough hands. And the probability of 3 things coming together at the right time and space is really, really low. So we don't see molecularities greater than 3, mostly unimolecular and bimolecular interactions. If a reaction occurs via a simple bimolecular elementary step, its rate law is overall second order. That's what I showed you here, right? If it's just a simple bimolecular elementary step, the rate law has to be second order. If a rate law is second order, can one infer that it occurs via a bimolecular step? So if I know that this is the rate law, Does it have to be bimolecular? And the answer is no. Right? More than one mechanism can produce the same rate law. And so you have to consider the total mechanism in order to derive the rate law. Last but not least, kinetic schemes often involve open systems. Open systems can transfer mass or energy. Therefore, there's no rule that the elementary steps must add up to the net chemical reaction. I found through the years that some students are told that this is a rule in a general chemistry class, but in general, that's not true. However, when it does happen, it does make your life a little bit easier. Okay, we're going to start driving some rate laws. And the name for this is sometimes called consecutive elementary interactions. It says interactions, but it should be reactions. Consecutive elementary reactions. A goes to some intermediate species, which I abbreviate I, and then I reacts and forms P. These are elementary steps. So there is a rate constant associated with each one of these, K1, K2. And the goal is to figure out what the rate law is. Right? The first step in that process is to write a rate expression for each species. So here we go. Step one is a unimolecular reaction. dA dt equals. I lose it in step one, it disappears, so I get a negative sign. I have a K1 rate constant times concentration of A. That is the rate expression for species A. For species I, di dt, I gain I if step one occurs. So this is positive K1A. Again, this is a unimolecular step, so it's just K1A. And in the second step, I lose it. Right? So the intermediate can react to form the product. I'm losing it. So it's minus K2 times the concentration of I. Last but not least, dP dt. I gain P in the second step. So it's a positive K2 times the concentration of I. Those are the rate expressions for each species. Now we need to solve these. We need to integrate these. And it's a complicated problem. These are called coupled differential equations. This one we can actually solve. This is an integrated rate law problem. Right? A to the minus K1T. So minus there. But these other ones are hard, right? So A depends on time. And you have to plug this expression into here, and then I relates to P. So all of these things are tied together. And if you take a DiffEq class, you learn how to solve these things. We'll talk some more about that later. But what I want to do at this point is give you some qualitative features of the solutions. So let's talk about that. Here's two different scenarios. In the first scenario, I'm imagining that step one is fast compared to step two. Right? And if you solve those rate expressions, here's what you get. Right? Step one is fast, so A, the reactant, quickly reacts and forms an intermediate, and then this forms the product here. In the second scenario, step two is the fast one. So my products, A, slowly decrease in concentration. They form the intermediate, which very quickly forms the product. Here's the question. What do you notice about the rate of formation of the product in both of these scenarios? Right? The green line. And if you look at them, what you might notice is that that rate of formation of the product is the same, more or less, even though these are very different. And the point that I want to emphasize to you is here. In both scenarios, the product formation is limited by the slowest step. In this one, step 2 is slow. So I quickly form the intermediate, and then this slowly forms the product. In step 1, I slowly form the intermediate, and then that quickly reacts. Right? So the overall production of product is going to be limited by the slowest step. And this is an important qualitative idea that I hope is familiar to you. It's called the rate determining step. The idea is that in a reaction mechanism consisting of multiple elementary steps, the overall rate is governed by the slowest individual step. Right? That slow one is what we call the rate determining step. So again, this is some reaction coordinate, right? Here are these different steps. Step 1, step 2, 3, 4, whatever, right? Step 1 here has the high activation energy. It's going to be slow, and this is going to determine the rate of reaction. Right? It's sort of described pictorially here. Right? It can be fast, it can be slow. It's the slow one that matters. This type of process, where you have some fast and slow steps, which are circumvented by a fast one, is a catalyst. Right? That's what a catalyst does. Okay, that was qualitative feature 1, rate determining step. Qualitative feature 2, students ask, well, what if there is no rate determining step? Right? And that's shown down here in this bottom plot. Right? Above I had, one step 10 times faster than the other. Here I set them equal. And you can see in this scenario that the rate of product formation is different than either of these two. Right? The intermediate is also clearly very different. And so my general answer to you would be it gets complicated. If you're interested in this kind of thing, take a DiffEQ class, right? Or possibly advanced PChem, and we can talk about how to solve these things. But it gets complicated. Last but not least, I could consider 2 different mechanisms, right? A to P or A to I to P. How could I differentiate those 2 things? How would I know that it goes directly from A to P versus A to I to P? And if you look at these results, right, if you had the same sort of rate constants, they're really not that different. Here's what it looks like if you form the product through an intermediate. Here's what it looks like if you form it directly through the product. So it's not clear exactly how you would differentiate these things. And what you might intuit is the giant difference between these 2 scenarios is this curve here. So the way you differentiate these mechanisms is either by making very careful measurements of these differences or identifying the presence of intermediates. And I think the moral of the story that I want to tell you is that kinetic models are always provisional. We say you're always employed in kinetics because the way these systems work is that people have one model for a certain reaction, and then someone comes along and finds a new intermediate that had not been previously identified. Or they measure the rate under a new set of conditions and they find some new slightly different behavior. And given that new information, we have to go back and revise our mechanisms. So you're always employed. I'm going to stop here. That's my summary of terminology and some qualitative features. And in the next video, I'll start to give you some more details about how to solve these equations.